Physicists have always been great at breaking matter into smaller and smaller pieces, and in 1968, physicists made a very important discovery. The protons and neutrons found in atoms were made of even smaller particles called quarks. There are 6 types or flavors of quarks. There are the up, down, strain, charm, top, and bottom quarks. A proton is made up of 2 up quarks and 1 down quark, and when you add their individual charges up, you get +1, the correct charge for a proton. Quarks cannot exist in isolation. They always need to have other quarks around. And obviously scientists have tried to separate quarks and hadrons, but it didn't work out, and here's why. Let's consider this quark-antiquark pair and think of the force between them as a rubber band. When you try to stretch them apart with a lot of energy, the rubber band does not snap. Instead, the energy is converted into new mass in the form of new quarks. Wait, can energy be converted into mass? It actually can, as stated by Einstein's famous equation E=mc². However, quarks seem to violate a very important rule called the Pauli exclusion principle. This principle states that no 2 quantum particles can have the same quantum state in a quantum system. All this means is that 2 quarks of the same type cannot exist in the same place at the same time. We just saw that 2 up quarks exist perfectly within a proton, so there must be some property which distinguishes quarks and hadrons. And this property is called color charge and was proposed by Oscar Wallace Greenberg in 1964. No 2 quarks can have the same color charge in a hadron, distinguishing them, and hence the Pauli exclusion principle is not violated. Inside a hadron, the quarks can have 3 possible colors: red, blue, or green. Antiquarks can also have 3 possible colors: anti-red, anti-blue, and anti-green. These quarks constantly exchange particles called gluons between themselves. A gluon, however, has to carry a color as well as an anticolor. Let's take an example. If a quark with the color charge of blue emits a blue anti-green gluon, it loses its blue color and becomes green. Think of emitting an anticolor as gaining a color. Now, if a green quark absorbs this gluon, it loses its green color and becomes blue. Think of gaining an anticolor as losing a color. Charge is responsible for the strong interaction, one of the 4 fundamental forces of the universe, and is also responsible for keeping quarks confined within hadrons. The theory which describes the strong interaction is known as quantum chromodynamics. Maybe quarks are not fundamental particles. Maybe they're made of something else, something smaller. And maybe this is not the end of our voyage into matter. No one knows yet, because particle physics still has a long way to go. So don't think that the story has ended just yet.